Okay, so let's start with a summary of last time. So last time we continued on with calculus of variations. So let's just remind ourselves a little bit of the framework. So given a function y of x, we introduced the varied value of y of x. Which we called y bar of x. And so that would be the original function plus some small modification, which we can write as some number that we can let tend to 0, and then some new function phi of x. So y bar of x is truly a different function than y of x. And then we introduce the variation and we call that delta y. And it's the change from the original function. So it's y bar of x minus y of x, which of course is just the epsilon phi of x part. So that's the variation of a function. It allows us to consider situations where what if the function was a little bit different? And ultimately that will tell us, those considerations will tell us what the function actually must look like for a physics problem. Okay. So after that, we found that if we wanted to find the stationary value of a function, where this capital F may depend on more than one function of x, and so the stationary value can be found by requiring that delta of the function is equal to 0. And that gave us the well-known conditions that for the function to have a stationary point, then the partial derivatives of that function must be 0. And that's exactly what you would have expected from just normal calculus. And then finally, we considered the case of stationary value given a constraint. So let's say that the constraint is given by some function of the variables that capital F depends on. So in this case, it could be a function of y of x and z of x equal to 0. So to find the stationary value of capital F, so this would be our constraint equation with the lowercase f. To find the stationary value of capital F subject to the constraint given by lowercase f, we can find the stationary points of what we call f bar, which would be given by the original f plus lambda times the lowercase f. And we call this lambda the Lagrange multiplier. And so we applied this. As an example, we did find the dimensions of a box that maximize the volume of the box, so that's finding the stationary point, given the condition that the area of the box is a certain number. So you have a certain amount of cardboard to make your box with the maximum volume. And so the restriction that the area must equal something is like the lowercase f equation, and the uppercase f equation is the total volume of the box. So we did an example where we found the total volume of the box subject to a constraint. Okay. So any question about that material? Okay, so the real reason for doing this variational calculus is because we're interested in the stationary value of integrals. The normal calculus already handles quite well finding the stationary values of a function. But that was just to get you familiarized with the formula. So today we look at the stationary value of an integral. So this is something that's going to come up a lot in the analytic mechanics. And the case is that we want to find some function, y of x, that minimizes an integral. So we will want to find a function y of x such that the integral given by, let's call it I, is going to be a definite integral from a point A to a point B of some function which we'll call L. And this function L will depend on the y prime, and x. And it's an integral over dx. So we want to find y of x such that this integral is stationary. So y prime, remember, means dy by dx. Okay, so as is, this sounds a little bit of an intangible problem. How could this situation possibly arise? Okay. So let me give you an example of an application where we would want to find y of x such that some integral is stationary. This is example 2.4 in the notes. Oops. And this is called the brachistochrone. This is a famous brachistochrone problem, which is actually the reason variational calculus was developed, was to solve this specific problem. So let's say that we have a point A and a point B. And we have a wire that we want to connect from A to B. And we have a bead. So that's a wire. That's a bead. And the bead can slide frictionlessly along the wire. And the question is, what shape of wire minimizes the time for the bead to slide from A to B? Okay, so obviously we have gravity pointing down. So maybe the answer feels like it should be a straight line, but you could easily argue, if you drop fast first, then the bead speeds up as quick as possible, and then it's going really fast on the flat part to get to B. So it's actually not trivial what the answer should be. In fact, it ends up being a complicated function. But it's not a straight line or a parabola or something pretty. Okay, so that's the physics problem that we're trying to solve. So if we frame this in the formalism of calculus, we should add a coordinate system Okay, can people hear me? Oh, what's wrong with this thing? Okay. Sorry about that. I'm unmuted. Yep. Okay. I don't know why it's booted me out. Because I have two computers running, and one of them seemed okay, and the other one got kicked out. Anyway. Okay, so the Brachistochrone. So the question here is to find the function y of x so that the time to go from A to B is minimized. All right. And I hinted that the answer will be given by finding the stationary value of an integral. But it's obvious that what we need to do is to write out the time that it takes to go from A to B under the force of gravity, right? So the total time for the bead to go from A to B is given by the integral from A to B of ds over v, where ds is some small elements along the curve, and v is the instantaneous velocity of the bead. So we need to make this presumably an integral over dx, and we also need presumably the function that describes the wire will somehow have to be in there. And we need to know the speed of the bead as a function of where it is on the wire. So let me add a new page. So the speed of the bead, oops. The speed of the bead is easily found from conservation of energy. Maintenance of progress. Yeah. I'm still having problems with my computer here. Okay. I'm worried my computer is going to reboot here halfway through. But, okay, so the speed of the bead is given by the conservation of energy. So the bead starts at rest at point A. So we can write that its kinetic energy, a half mv squared, and so the v is the v that we're going to need in the integral. That is given by mg, and then the change in height. Let's say it started at YA, and then its current position is Y. So that gives us the speed of the bead as a function of Y. Alright. Don't know why I got booted out again. Hopefully it stops happening. And this example will end eventually. We're almost there. Okay, so remember the integral that we need is t is the integral from a to b of ds over v. So we've expressed v in terms of x and y, in this case only y, so we need to change the ds. So ds, we can use a trick. So you'll agree that ds is the square root of dx squared plus dy squared. Right? ds is an arc length along our line, our wire. And so that's infinitesimally given by the square root of dx squared plus dy squared. So here we can do a little bit of mathematical trickstery. And let me divide everything by dx. So I have dx squared divided by dx squared underneath the square root, so that turns into a 1. And then here I have dy squared divided by dx squared. And then I can factor out a dx out of the square root. And so I can write this as well as 1 plus dy over dx all squared or using our prime notation as the square root of 1 plus y prime squared dx. Okay, so that's a little bit of trickstery to get the integral in the form that we like it. So now the total time, if we plug all of this in, t, which was the integral from a to b of ds over v, is the integral from a to b of, so our ds is this 1 plus y prime squared dx. And then our v is square root of 2g times ya minus y. And so now our problem is that of solving, finding which function y makes this integral a minimum, or in our case minimum, but in general stationary. So the function L, which I'll write as L of y prime and x, is the integrand of this thing. So that's square root of 1 plus y prime squared divided by the square root of 2g ya minus y. Where my g's and y's look very similar. Okay. So I rebooted my computer. Hopefully it works. Nobody else is getting kicked out of just me, right? Something to do with this computer. Well, let's resume, I guess, until the next crash. Alright, so in this infinitely long example, we showed that it might be of interest to find a scenario where you need a function y of x, and then some function of that function y of x, its integral needs to be minimized. And that's exactly what you need to do in this Brecht-Histo-Krohn problem. So we want to find conditions on the function L that depends on y, its derivative, and x in general. We want to find conditions on L such that the integral given by I, integral from a to b of L, it depends on y prime x dx, is stationary. And we'll go back and solve the Berkisto problem as either a assignment problem or a tutorial question on Thursday. Okay. So we call this whole integral here, we call this a functional. We want to find y so that the functional I is stationary. And we also have note. We have a boundary condition that y evaluated at xa must be equal to ya, and y evaluated at xb must be equal to yb. So you can see how now variational calculus is, the concept seems to make sense of you need to consider all the possible functions y of x and then select the one that matters. So you want to be able to consider a mechanism for considering different possibilities for y of x. And so those are varied functions y of x. So that's how it all kind of comes in. So consider Okay, so this is Ryan on the other computer. It's clear that there's a problem with Blackboard Collaborate. I think it's because I have a special link when I join the session for the teacher where I have like a super controller or everything. If I go to the Blackboard website now, I can't even log in. So I think there's actually something wrong with their servers. And I'm getting a bunch of errors that, I can't connect to. So I guess I'll agree that we should call it a day with Jacob. So I apologize for that. You guys can hear me right now when I'm speaking, right?
Yep.
Yeah. Now, I'm having trouble downloading the session file for the teacher, and I've downloaded it 4 times. Like basically, every time I reconnected it, I can't get on. So let's just say we'll cancel the class for today, and then I'll start back at the end of the example on Thursday. And you guys can take this time to work on the assignment if you want. I apologize for this. All right, so I'll talk to everyone on Thursday. Feel free to email me if you have questions about the assignment. Oh, I can't even stop the recording. All right.